Hi, everybody. I am going to be recording a quick lecture for you to watch on Monday since I won't be uh, around on Monday and will be away for the week. I hope that you all are going to be having a great Thanksgiving break, getting some much needed rest for the end of the semester. But I am going to do a quick video here for you now. I am recording this on Thursday evening before break, so I am not quite sure how far we'll get on Friday, tomorrow for me, in lecture. So I'm going to start with phase portraits. I think we will have gotten through some of this, so you can kind of skip ahead to wherever we get to in class on Friday. But I'm going to talk a little bit about phase portraits here, and then get into solving first order differential equations afterward. But to start, I want to talk about how in chapter 1 we introduced the concept of slope fields as a way to visualize some vector field and visualize kind of first order differential equations like dy dx equals y minus 2x, for example. And this what was something where we could plot out some space x and y and say at any location, say, let's just call this 0, 0 down here in the corner, and then, I don't know, some 1, 1 up here. We would then say going, or maybe I'll make this 2, 2, and 1, 1 here in the middle, something like that. And we would be able to figure out anywhere in this space what the slope would be. So when when x equals 1 and y equals 1, we'd get 1 minus 2, and so we'd get a minus 1 slope there. And then depending on where we were, if we were at x equals 0, y equals 1, we would get a slope positive 1, and we could plot this all out and see that this slope field does it increases up like this when y gets really big at a constant value of x, gets larger and larger slope like that. And then at some point, when we go towards large enough values of x, we would have it turn over. And of course, we could figure out exactly when does this slope equal 0 by solving this, and that would be when y equals 2x. So there would be a line here of slope equals 0 uh, when we follow this line y equals 2x upward. And then when we move beyond that line, we would see that the slope turns over and starts going down like this. And we could plot out these vectors. And of course, we did this in cases where we would teach the computer how to do this, but right now I'm just doing a very rough sketch. And the one point of doing this was to say that if we maybe picked some initial condition for this system, we could describe how it might, or like what a trajectory in this system might look like. And so it might kind of follow this way, following these slope field lines down like this. And now I want to extend this idea of visually plotting out how these systems of differential equations evolve. I want to extend this to maybe coupled differential equations like we studied when we were doing some of our linear algebra. So, for example, a pair of coupled differential equations might be dy dt equals 4y, and maybe dy dt equals x. These are two differential equations, and you can see that since x depends on y and y depends on x, they're coupled together. And we could plot out on some set of axes, x and y, and say, well, if we had some initial condition, say at like something like y equals 1 and x equals 0, like this, we could say, well, if x equals 0, then there's no change in the y value at that location, but the x value will increase somewhat this way, and the magnitude of that, of course, depends on how high up in y we are. And we could then say, well, if we get pushed over to this side and now we're over here somewhere, well, now we do have some dy dt because we're at some positive value of x. We're going to be now pushed upward, and then that's going to cause us to be pushed even more further upward because anytime we get moved towards larger x, we want to move even, or sorry, we want to move even more up in terms of y. And as we go towards larger values of y, we're going to move towards even larger values of x. So that's what's going to happen over on this side. But if we happen to start somewhere over here in a negative value of x, then our y coordinate is going to actually be pushed downward. And of course, since we're in the positive y quadrant still, we would be moving still in the positive x direction. And you'd see we'd get something like this, some trajectory, something a little like this for that. Um, and if you looked at different other locations, you'd get perhaps different trajectories. If you moved too far over in x, then of course we know that in general you're going to keep moving uh, to the right and down because that's what was happening over here, and we haven't really changed much about how that happens, but we are going to change that. Eventually we're going to hit this axis before we turn over, before we hit the y-axis, which would cause us to start turning over and moving back upward. We're going to instead hit the x-axis here first and move us from positive values of y to negative values of y, which is going to change the direction that we're going to move in the x direction. So now this trajectory would look a little bit more like this. And if we just fill out this space, we'd get something that looks a little like this if we started over here. And if we started somewhere at a large enough value of x, we would get something that looks like this. And this now is really telling us something about how this system is going to evolve. And there's kind of different areas of this system that if you start in certain areas, you're going to get certain types of behavior. And if you start in other areas, you're going to get other types of behavior. And if we plotted this all out carefully, hopefully I can draw this. I want to go through the origin like that. And I'll do another line over here. In this specific case that I'm using as my example, we end up getting these lines that separate regions of behaviors. And so we could draw more trajectories in here, but any trajectories that start kind of in this almost quadrant here, defined by the region in between these two pieces of these lines, are all going to behave quite similarly to each other. Same thing's going to happen over here and over here as well. Uh, so we get these regions of similar behaviors. I want to explain a little bit about how we could predict some of this. First, we can notice a few things about this system of equations. One thing that you might want to look for first is where do these derivatives equal 0? And that will tell us if both of these derivatives are 0, that point, whatever point in space that represents, is going to be a stationary point. Meaning that if you started out at this location that had this property, then you're not going to move away from that location. You're going to stay there. You could also call this an equilibrium point of some sort. And quickly looking at this, we can identify that the only place that that's going to be true is at the origin. That the only place it will be true is that x equals 0 and y equals 0 right here. So if we have that, if we started our position exactly at the origin, we're not going to move away from it. But if we started anywhere else, we would move in some direction. Um, the other thing we can try to figure out is maybe what are these lines in the first place? How can we determine where those might be? And to do this, I'm going to actually rewrite our system of equations into kind of a matrix form, similar to what we saw when we were doing linear algebra. In this case, of course, dx dt, which I'll say is x dot, is going to be dependent on y and not on x. And dy dt will depend on x, but not on y. So our matrix will look something like this. Okay, that looks relatively simple. Of course, it's not quite a diagonal matrix, meaning that the main diagonal are not the only non-zero elements. In fact, it's exactly the opposite in this case. So what we would need to do to solve something like this is to maybe figure out what are the eigenvalues and eigenvectors of this equation. And if we do our classic strategy of taking this matrix and subtracting lambda times the identity matrix and taking the determinant, we would get lambda squared from minus lambda times minus lambda, subtract minus 4, subtract 4, set that equal to 0, we would see lambda squared equals 4 or lambda equals plus or minus 2 are our eigenvalues. And then if we use our eigenvalue equals positive 2, we would get a equation saying that we'd get, let's make sure I'm saying this all correctly, we get minus 2x plus 4y equals 0, or x equals 2y. So then v1 is, let's see here, let's just use 2, 1 as our vector. Well, notice that this, we think about this as kind of the equation of a line. We get, for every 2 units of x, we get 1 unit of y. Well, that's this line. And in this specific case, we also have a positive eigenvalue, which is going to tell us that that things along this line are going to be moving away from the origin. And of course, we could do the same over here, like that. They're going to be moving away from that origin because of this positive eigenvalue. If we look at the other eigenvalue here is going to be lambda 2 equals minus 2. If we plug that into our equation, we would get, remember this is minus lambda here, so then we get positive 2x plus 4y equals 0, and then we'd get that x equals minus 2y. And so now, for every positive value of x, we go down to, let me make sure I'm saying this right. No, that's where I'm getting myself mixed up. So this, let me just write out the vector. This goes minus 2, 1, like that. And this is going to represent this other line here. So then we go for every 2 that we go backwards. That's the way to think about it. We go up 1 in y. And in this specific case, so this does represent this line, we have an eigenvalue that's negative, and so these things are going to be moving towards the origin, like this. Oh, and of course, when we look at this, we see that trajectories near those lines are going in the same direction, that when we are near this line here, we're moving towards the origin, but when we come towards this line here, we move away from the origin, like that. And so with this idea, we've identified the lines that separate regions of space that have different types of trajectories. I'm going to call those lines separatrices. or another, and it's a single one is called the separatrix. And they have some different behaviors if these trajectories tend to move away from the line, as in say like this line here, the trajectories start maybe close and then move away from that line. Those are going to be called repulsors, repulsive separatrices. And so this one and this one here have trajectories that start close and then move away from them. And the other two here have separatrices or are separatrices that are attractors that have trajectories that move towards them. And then you can also describe equilibrium or stationary points as either attractors or repulsors as well. Although in this specific case, our one stationary point at 0, 0 is neither because it has some trajectories, some lines here that move towards it and some that move away from it. So it is not a clear case of being either a attractor or a repulsor. I wanted to, let's see here, very quickly share how we can look at this in terms of our, in terms of plotting these things out. So here I have created a grid of points in X and Y, and then calculated X dot and Y dot and created a stream plot. This is something that we did way back in chapter 1. Um, to visualize this, and you can see these trajectories and these two sets of separatrices here and our stationary point at the middle. But you can really see how these trajectories, when I plot them out nicely instead of just sketching them by hand, these ones are starting close to this separatrix and moving away from it, and then going towards this other separatrix down here. So this is how we could create one of these phase portraits. Uh, okay, so then, am I here? Yeah. Okay, so one thing we can also do is think about other types of differential equations that we can represent in this way. One other type that we can do is maybe instead of two coupled differential equations, we could take one, and of course those ones were both first order differential equations before. So we can have two first order differential equations that are coupled together, and we could represent them like this. We could also take something like a second order differential equation. And as my example here, I'll use a damped oscillator. So something like this equation. Of course, we've seen something like this before. If we ignored that velocity dependent term, this would just be a simple harmonic oscillator. But if we introduce this, this introduces some damping. But what we could do is define another variable, here I'll call it v because it does represent the velocity, as this variable v equals x dot. And then this x double dot, if I express it in terms of v, comes just now v dot. And that is minus 4x minus v. And then, of course, I'm going to just flip this equation around on its head to write it like this. And this is now a set of first order, meaning that we only have single derivatives showing up, coupled differential equations. So now we're basically in the situation we were just in before. And except now instead of x and y, our variables are x and v. And we could, of course, write this out as something like x dot v dot equals, now here, x dot is just 0, 1 times x v. So x dot just depends on v, and v dot depends on, so we'd have minus 4x and then minus 1v like this. And so we would be able to figure out here, like, what are things like the eigenvalues and eigenvectors of this equation, and things like that. But otherwise, we can come up with this plot and say v versus x. And of course, we can go back to how we were doing it originally and saying, like, okay, well, uh, where would these things be? 0. Well, x dot is only 0 when v is 0. So when you're on the x-axis, and then when v is 0, the only place that v dot would be 0 is when x is 0. So again, our only stationary point is at the origin. And we could plot out things like, okay, what happens when you have a positive v but 0x? Then you'd have a increase in your x coordinate, and v dot would be, well, I guess, sorry, no, v dot would be negative in this specific example. So something like this, points somewhat down and then to the right. And we would continue to go around like this, and what we would see is that this solution actually kind of spirals inward towards this center, like that. And we end up getting kind of this oscillation between having large values of v and larger values of x, and going down with this decaying oscillation, which is really what we saw when we solved this style of damped oscillator in the past. Now we get decaying oscillations. But what would happen if we removed that damping term and just looked at something like this, minus 4x, and then we would define, of course, x dot equals v, and v dot is now minus 4x. And so then this would be our system of equations. We do the exact same thing again. We say v and x. And if we plotted this one out, what we would see, of course, we get that same stationary point. But in this case, now our amplitude of oscillations do not change at all, and we would go around in a perfect circle like this. And it's important, of course, I'm not great at drawing circles by hand, but the radius that we start at just depends on the amplitude of these oscillations that we're starting with. And as long as our damping is 0, that oscillation amplitude is not going to change. So I can also share, I think I have some of these. So here's that first one where I have the damping in there. We can see that we've got these all these different initial conditions that are represented by these different trajectories. What's going to happen to them is they're going to spiral inward, and their amplitude of these oscillations is going to decay. If we, and then let's see here. Let me show if we remove that altogether, what we would get there we go. Now we have these circular ones, and they don't quite look like perfect circles just because the scaling on these axes is somewhat off. Let's see. And I'm not going to worry about that here now, but if I forced these axes to be square, you would get perfect circles rather than what currently looks like an ellipse, just due to the different scaling on these axes. Okay. So that is kind of a brief look at these phase portraits. I guess, probably have said a little bit more about why do we call them phase portraits. Phase is something that we've used in the past to describe kind of the state of some system. In particular, we used it to talk about the state that an oscillator was in, like the phase being where it was at in its cycle. But more generally, phase can mean just talking about what is the state of the system and what variables describe that state. So in this case, our variables that we used to describe the phase were v and x. And we were creating a phase portrait showing how those v and x changed as we moved around in this diagram and talked about how this system would evolve. Um, but these variables here are both, in this case, dependent on time. Time is not one that shows up in this diagram. So we can't really say exactly how fast this system will move through this evolution that we see in this phase diagram. It just shows you kind of simultaneously what a bunch of different possible trajectories would be given different initial conditions. So this would again represent another different initial condition and its trajectory around this space. And you can see all of them kind of simultaneously existing, even though the system, of course, with one set of initial conditions would only follow one of these paths. Okay, so grab another sheet of paper here. That's all I wanted to talk about with phase diagrams. I did want to spend a little bit of time introducing some other ways to solve differential equations. And in this specific case, we're going to learn a nice method for solving first order linear differential equations. So those are the equations that have some form that looks like this. Uh, and in this case, if we have, you could imagine that there was some, or sorry, let me back up. So this is our derivative of whatever our function y is, and y here could be a function of x and some other constants and things like that. And this is the derivative of that function with respect to x. And then we have some function of x, could be any function involving x, times the function itself, and then that could be equal to some function of x. So that's what this form really represents. You could imagine that there was maybe some function of x in front of the y derivative as well. But in this case, you could always divide the entire equation by this q to get it into this form in the first place. So we're always going to assume that we get some equation that we could at least put into this form if we don't already have it in this form. So I'm going to show you a general solution for any first order linear differential equation that has this form. So one thing I want you to notice is that here now we have the derivative of y plus something, and sometimes I'll drop the function of x thing here, but p is still always a function of x. So you've got the derivative of y plus something times the function y itself. And of course, that's equal to something over here. But I want you to just look at this left side and recognize that this looks a little like a product rule. That when we, so if I say that we have some derivative of that derivative with respect to x of two functions multiplied together, we would get something like a prime b plus b prime a, like that, right? For the product rule. And so if I imagine that my, let's just replace here, let's replace a and b with, I'll write it out in terms of some function I and y, this thing that we have here. And if we wrote it that way, we could get I y prime plus I prime y. And this looks sort of like the left-hand side of that. If I could multiply this whole thing by I. And so I'm just going to go and do that. I'm going to take our original equation and multiply it by whatever this function of x that I'm going to call I is. So then we get p I y equals I f. So this is literally just that first equation, the form of it, and we're going to write it like this multiplied by I. So now I've got this term here, and now this thing has to be here. So I could say so let's say PIY equals I prime y. This is what would need to be true for this to equal that. And now all this is so that we can get something that looks like a product rule, so we can convert it back into a derivative of I times y. And all of that is, again, so that we could just integrate both sides of the equation so that we can just integrate f of x and solve for y. That's all looking a little bit ahead of where we're going. So this PIY should equal I prime y. Of course, we can just cancel these y's. So I'll say PI equals I prime, and we end up with another differential equation. This one is, again, first order, because we now have I and I prime related to each other. But this one's easier. This one is separable even. Let me write that out a different way. I could say I prime over I equals P. Or di dx over I equals P. And if I break apart this derivative into its components, I would get di over I equals P dx. And here's where I'm going to integrate. I can recognize the thing on the left will just be log I. The thing on the right, I don't know what p is. I know it's a function of x, so I can't evaluate this integral. I'm going to leave it as is and say that this is the integral of p with respect to x. But I want to know what I is. So I'm going to take the exponent of both sides here and say that this I is e to the power of the integral of p with respect to x. And this thing we call the integrating factor. And this is going to allow us to do some powerful things and solve this differential equation that we started with. So if you have any equation that looks like this, you can multiply by this function that we just found, I, like that. And then because we chose this function carefully to make this, what I'm about to do, true, we can factor this uh, into just a derivative like that. We chose I very carefully so that we could do this. And this becomes IF on this side still. Now I'm just going to integrate both sides with respect to x. So I'm going to integrate here and integrate here, dx. And the integral of a derivative, of course, is just going to give us IY. And on this side, we're going to get the integral of IF dx, whatever that happens to be. And so our final solution for y is 1 over I, integral of IF dx. And that's why we go through all this effort to find I in the first place, is because it will allow us to do this. Now, I did jump a little haphazardly ahead when I should have maybe described a little bit more about what I was doing with this I. So here, sorry. I is, remember, e to the integral of p dx. P is whatever goes in front of this y in this equation when we write it in this form. Whatever goes there, it could just be some constant value, in which case this integral, of course, becomes quite easy to do. It could be some function of x. It could be a polynomial. It could be sine of x. It could be whatever it is. You integrate that. You raise that, or raise e to that power, and then that's your function of I. Note when you evaluate this integral, you don't need to add like a plus c for when calculating this integrating factor. Now, it's not to say that you can't do it. You could, and you would end up getting the same answer. So let's say I got e equals some e to the integral p dx. I'll just say I'll make up a new function. I'll call it g of x, like that. Uh, and let's say I did add a c. Well, of course, we could separate this out. That's e to the g of x, e to the c, just from exponent rules. And then when we plug it in here and here, this constant factor, we could factor it out of the integral, and it's going to cancel with the factor in the denominator here. So no matter what we did with that constant value, it is going to cancel because there's an I here and an I in the denominator. So it won't matter in the first place. So we can just ignore it altogether and say, let's just choose c equals 0 as our integrating constant, because it won't matter no matter what we choose. But when we evaluate this integral, we do need to account for the plus c. So we will get, in this case, 1 over I, and then let's just say that this becomes some, not f, so, I don't know, some h of x plus c. This one is going to be important because we might have some initial condition like y of 0 equals 3 or something like that. And this will help determine what that c is to find a specific or particular solution to our differential equation. This is our arbitrary constant for our first order linear differential equation. We know for a first order equation, we should have one arbitrary constant, and this is where it's going to come into play right there. So let me do an example of doing this. So I'll say dy dx, sorry, plus y over 2x equals e to the x over square root x. So in this case, we get p of x equals 1 over 2x. Let me take the integral of p dx. It's the integral of 1 over 2x dx equals 1/2 integral 1 over x dx, or 1/2 log x. Well, I'm going to use logarithm rules to also make this log of x to the 1/2 power. Because then I want I to be e to that thing. So e to the log x to the 1/2 power is just x to the 1/2 power, or in other words, square root x, like that. Okay, so that wasn't too bad. If we then say I can multiply all this stuff, so we get square root x dy dx plus square root x y over 2x equals e to the x. I could then say, okay, well, I got square root x divided by x. This becomes square root x dy dx plus y over 2 root x equals e to the x. And you might even recognize that this here is the derivative of root x. So then we could say that this is d dx root x y equals e to the x. Now, you don't even really have to recognize this intermediate stage, since we specifically carefully crafted our formulas. I will always be whatever you calculate it to be, and then this thing here will always be I times y inside that derivative. So you could just jump right to that step without doing this intermediate stuff I did. But then what we can then say is that we can integrate both sides and get root xy equals integral e to the x dx. Of course, we know that's just e to the x, and that y becomes e to the x over root x. Okay, that wasn't so bad, but what we can do now is just double check. Does this solution that we've come to solve our differential equation? Remember, it should have been, or sorry, here it is. Should be dy dx plus y over 2x equals e to the x over root x. So let's calculate dy dx for this equation and say, sorry, let me back up a second because I should technically have said that this integral is e to the x plus c, and then that this would be e plus c over root x, like that. Right? Make sure I'm doing this most correctly for you, because this constant could matter given some initial condition. So if we did that, we take this derivative, we would get, let's see, if we keep the top by itself and then take the derivative of the bottom, we would get x to the 3 halves, we'd get a minus 1/2 out front, like that. And then if we did the derivative of the top, keeping the bottom constant, we would just get e to the x over square root x, like that. And then if we said, let's see here, what is our differential equation? So we have this result. Let's add to that. So we have e to the x plus c over x to the 3 halves minus 1/2 times that plus e to the x over root x. That's our dy dx. Then we have to add to that plus y over 2x. So I'll put 1 over 2x out here, and y is e to the x plus c over root x. And c, does this equal e to the x over root x? So let's see, we get a 1. So this becomes, okay, so x times root x, all of that in the denominator becomes this becomes x to the 3 halves. And then we get e to the x plus c, and then over, here, let me just write that. E to the x plus c over 2 x to the 3 halves is this term. And then we'd have minus exactly the same term, e to the x plus c over 2 x to the 3 halves from here, plus e to the x over root x. These two terms cancel exactly. Sorry, I'm doing this all a little off camera. And what we're left with is e to the x over root x, which is what our original differential equation tells us it should be. Cool. So that all works well. So I'm going to end the video here because I'm going to record one other video of a walkthrough of a exercise that you can do at this point. So hope you all have a great break, and I will talk to you all. Well, I'll see you tomorrow, but I will also talk to you all after break, and hope that you have a great Thanksgiving.